Hello students, this is a brief tutorial that explains how we concluded the modern model of the atom, which often we refer to as the quantum model of the atom. This is the next step after the Bohr model and improvement upon it. Recall these were the main conclusions of Bohr, saying that electrons traveled in circular orbits. They were quantized, they had a set defined energy. The closer the electron was to the nucleus, the lower in energy it was. However, this very shortly was proven to be a failure. Bohr's model only correctly matched the line spectrum data from hydrogen. Only one electron systems matched mathematically the line spectrum that we got, the Roy-G-Biv, the individual bright colors, only matched for hydrogen. So a model that can only explain one element when at that time we knew almost of 100 or so, very limited. So we knew that improvements needed to be made. Well, the quantum model really came about after the discussion about the dual nature of light. And so remember, we talked about these things. And in realizing that light can have a double personality, that sometimes it shows more of its wave side, like in constructively and destructively interfering, like in the double slit experiment. Sometimes it's showing more particle nature, like in the photoelectric effect. And realizing this, the next question, of course, was, well, what about matter? Does matter also have a dual nature? And mathematically, after experimentation and mathematical work, it was found and concluded that an electron has a perfect 50% wave, 50% matter personality. So that's why the next advancement with the atom came from a better understanding of light. So, the quantum model of the atom. It succeeds in that it views the electron as a wave. In fact, a standing wave. We're all familiar with a guitar string that is secured at both ends. But if you pluck the string, it moves back and forth and back and forth and back and forth. It's really hard to tell exactly where the string is at one moment in time. That's a standing wave. So, in the electron, I know, we've talked about waves as crests and troughs, but we need to view it now as coexisting in a bunch of places at the same time. That's how we have to move forward understanding about the electron. Also, a new term. In the quantum model, electrons are found in orbitals. These are probable locations, not exact, probable. And that is just good enough for us. The Heisenberg uncertainty principle. We cannot know the exact position of an electron. Now, the Heisenberg uncertainty principle officially says that you can't know both the momentum and the position of an electron at the same time. You can only know one, but really what we can infer is there's no way for us to pinpoint exactly where an electron is. To do that, we need to shine light on it. All of our technology, to be able to see things, microscopic things, we need light. Well, if we shine light on an electron, we know we're giving it energy, and it'll move. So, we try to see it again, and guess what? We move it. Try to see it again, and we move it. So right now, we are limited technology-wise. We cannot know exactly, but can predict with pretty good certainty. And that predicted location would be an orbital. There's something called the Schrödinger equation, which mathematically predicts how likely it is to find an electron a certain distance from the nucleus. So you solve this equation for a certain distance, and if the likelihood is pretty good, put a dot there. And if it's not, we're not going to put a dot. So what we end up doing is solving and then getting these patterns of dots where we are pretty sure we're going to find an electron. Well, instead of this kind of coded series of dots, we shade it in. And that shaded in region of space is what we call an orbital. And there are 4 basic letters that describe the orbitals: S, P, D, and F. These were chosen after some spectrographic results, but it's not necessary for us to know why. Now, remember, we live in a 3D world, so we have our X and Y, but also our Z axes, and that's how we usually draw it. That's the axes that would be coming out of the paper toward you. So the X and Y is flat and the Z comes out at you. All right. The S orbital has a spherical shape. The P is double lobed. And what we find about p orbitals is they are found on the axes. So I'll just draw one for us. So, kind of like 2 petals of a flower. And I'm just going to shade it in because that would be where we would find electrons. So the S is spherical. The center of it is based on the nuclei. The P is kind of an infinity sign, if you will. And the center would be the nucleus. The D has basically 4 lobes. And the F has at least 6, usually the basic is 8. So if you can just imagine, petals of a flower and then X, Y, Z axes. Now, these are not paths. They are locations where we find electrons. So if we could freeze the atom in the S orbital, the electron or electrons is going to be found somewhere. P, D, and F as well. Each orbital can hold up to 2 electrons. It doesn't mean it does. The potential is just there too. So this can hold 1 or 2, 1 or 2, 1 or 2, 1 or 2, or be empty. All right. Well, let's talk further. So these are orbitals. Well, the S orbital, could we take that sphere and rotate it in any way and get a different orientation? No. I mean, a ball is always going to look that same shape if we twist it. So there is only one S orbital. But let's talk about the P. Well, the P, as I said, mathematically is found to reside on the axes. Well, we have 3 choices. It could rest on the x-axis. It could rest on the y-axis. Or it could rest on the z-axis. And if we would freeze the atom, however we're looking at it, the P will be look different to us, a different orientation, a different presentation if it's on the different axes, if we would freeze the atom. So from this, there are actually 3 p orbitals. I'll show you a picture in a moment, but the D actually has 5 different orientations. So there's 5 d orbitals, and the F has 7. Now, after the SPDF, we do have orbitals that follow the alphabet, so G, H, and I. However, even with excited electrons, we're rarely going to be visiting these, but they do exist. Okay, so some terminology for us. What we understand is that we have our nucleus, and then there are distances from the nucleus where we're going to find electrons. And I know this looks awfully like bored, but they're not orbits. They're just distances from the nucleus where we're going to find electrons. Now, these layers, if you will, we call energy levels. And energy levels are just set distances from the nucleus where we find electrons. So this first distance we would call the first energy level, then the second, then the third, then the fourth, then the fifth, sixth, seventh, eighth, and so on. Now, energy levels are made of sublevels. And the sublevels are made of orbitals. Okay, so the previous set of drawing that I had, oh shucks, oh, just right here. Okay, so orbitals make up sublevels. The s orbital makes up the s sublevel. The 3p orbitals make up the p sublevel, and the 5d orbitals make up the d sublevel, and the f orbitals make up the f sublevel. All right, so if we go back to this. Okay, so sublevels. We have S, P, D, and F. Okay, the number of orbitals. The S has 1, the P has 3, the D has 5, the F has 7. Each orbital, remember, holds 2 electrons. So, the electron capacity. The s sublevel has 1 orbital. Each orbital can hold up to 2 electrons. So the s sublevel, the electron capacity is 2. The p sublevel has 3 orbitals. Each of these can hold 2, so that gives a capacity of 6. And then 10 for D and 14 for F. So each of these can hold 2. That's how we get this total electron capacity. All right. Energy levels are made of sublevels. Sublevels are made of orbitals. So if we were to map what sublevels are in the different energy levels, if you have ever made a model of an atom and placed electrons in their different, I'm not sure if you call them orbits or shells, not sure. Well, we call them energy levels. And if we just want to map out the first 5. So energy levels are made of sublevels. And let's talk about total electron capacity. I bet these numbers might be familiar to you. So whenever you made models of atoms and put your electrons in the layers, you were restricted with how many you could put in each layer. The first holds up to 2, the second, 8, the third, 18, fourth is 32, and the fifth is 50. So where do these come from? Well, if we remember that, what we just outlined, energy levels are made of sublevels. Okay. The first energy level can only accommodate up to 2 electrons. So what sublevel must be there? An S. Because an S can only hold up to 2. It couldn't be these, because then the first energy level could hold more than 2. How do we get 8? That must be a combination of an S and a P, this holding 2, this holding up to 6. How do I tell the difference between the S that's in the first energy level and the S that's in the second? There's a really common notation where we put the number of the energy level in front of the sublevel. So the S sublevel in the first energy level, we would call 1S. But in the second, we would call 2S. I'm going to make the different sublevels different colors. So let's say the P, I'll make blue. It's in the second energy level, so we're going to call that 2P. Let's just sketch then a drawing of this. So if I have my X, Y, Z axes, well, this first distance from the nucleus, that's where I'll encounter my 1S. So that's the region where I will find possibly up to 2 electrons coexisting, moving in some kind of way in here, kind of like a standing wave again. Then in the second distance, the second energy level, I'm going to have a 2S. Now the S is always spherical in shape. Oop, purple. Is always spherical in shape. Always has the same electron capacity. So it's the same shape, but a different size. It's further from the nucleus, but it only still can hold 2 electrons. So since these electrons are further, we say they have a higher energy. Okay, then P. Now, remember, there are 3 different P orbitals. So this would be if this is the x-axis, the Px, that can hold 2. The Py, that can hold 2. And the Pz, that can hold 2. So altogether, the 2s and the 2p, that can hold 8. So how do we get 18? Well, what combination can give us up to 18? It must be a 3s, a 3p, and here's where we can introduce a 3d. So 2, 6, and 10, that's how we get our total of 18. So if we want to try to construct this, in our third, that's where we'll have a sphere with 2 electrons. We'll have the P that can hold up to 8, and then we have or up to 6, and then we have our D, which can hold up to 10, 5 different shapes, each with a basic 4 lobes. There would be 1, 2, 3, 4, and then our donut. 5. Oh, I guess I need to show us the D, huh? So here is a good drawing. So here would be a 1s and a 2s, a 3s. So same shape, just different size. This is showing us the 3p orbitals. Collectively, that's the p sublevel. Then we have the 5d. And above it, those are just showing, the solutions of the Schrodinger equation that we shade in eventually to get these shapes. And I was referring to a donut. That's the one on the far right. So D has 5, and then your F, beautiful those are. Again, not paths, just areas of space where we're going to find an electron. And the G, even crazier. So who would have thought that our beautiful atom is kind of this beautiful just flower? All right, and then in the fourth, we would have a 4s, a 4p, a 4d, and a 4f. That's how we get our 32. And then the fifth, 5s, 5p, 5d, 5f, and here's where we'll have our 5g. And that's how we get a total of 50. Whew. So, very, very different from Dalton, from Thomson, Rutherford, Bohr, And if anything, we've just found more validation. This was late 1920s. We found more validation that this is how we need to view our nuclei, very dense, positive proton, neutron, but our electrons are in these gorgeous, mathematical predicted areas of space. So, quite beautiful. Where we're going next is to learn about electron configurations. How do we exactly map where the electrons